So thank you for joining us in the final presentation of this series of NVH. This looks at NVH real-world analysis, so we've got a number of failed components to share with you, and we're going to discuss how we've used NVH to pinpoint those vibrations.
The first example of where NVH can be an incredibly powerful, intuitive tool came about quite by accident. It's a 1.4 gasoline petrol Golf Mark IV, and I'd recently fitted some new tyres. I had no reason to believe there was an issue with this vehicle, but we were doing some R&D, and during a test drive I noted that there was a particular issue with an E2 variation in vibration. It wasn't consistent. It seemed to be particular to a certain engine speed, and you'll see from the graph we're going to have a look at in a moment that the gear ratios, engine speed, road speed, gear ratios, final drive were all entered, so we knew exactly what load speed range the vehicle was at. And you can see this rather high E2 event. So Steve, perhaps we can have a look at this.
Frank, I got there, you 46 miles per hour, 2,700 RPM.
The interesting thing for me here is if you look at engine speed and road speed, it's pretty consistent. There is very, very little change. But at a particular point, E2 seemed to pick up. Now, I was quite puzzled by this because the vehicle was quiet, no vibration I was aware of, no issues. The only issue I was aware of with the vehicle was a diagnostic trouble code relating to EGR flow. And it hadn't been an issue with performance, but it was a hard fault. We couldn't clear it. And I didn't relate the two things. So what we then did was, I thought, well, it's twice the frequency. If you look at the frequency of this event at E2, the engine was running around, for simplicity, around 50 hertz. The E2 event was nearly double that value, around 100 hertz. I was thinking, what is running at twice the frequency of the crankshaft? And I thought, well, it's got to be an ancillary. It's got to be something on the front end. So then returning to the workshop, we then did some visual examination. And to be honest, what I found really shook the foundations of my belief, because it was a critical fault whereby the timing belt guide had separated from the pulley. So the pulley is here. This guide had actually separated and, for want of a better word, was hovering in no man's land within the belt chamber. Additional to that, we did find a bearing, an excessive bearing noise from the serpentine belt guide. So that certainly was adding to some of the vibration and noise. Because we'd lost the guide, the belt was able to drift and come in conflict with the timing case cover and the back of the engine, separating part of the belt material. And that belt material then embedded itself on the tension pulley. And you can see here that there are indiscriminate lumps of rubber is the best way to describe it. Some are more aggressive than others. Now, my conclusion to this is we've found the cause of the problem. So why is it that this vibration, this E2 event, appeared to be more prevalent at a certain speed? And I put that down to resonance, where perhaps the effects of the belt depositing on this pulley, coupled with the effects of the bearing that was in the process of failing with this pulley, those two forces add together, produce this peak. The other very interesting thing about this is how did these two events then relate to a DTC for EGR flow? Well, that comes down to this part of the problem. The timing belt would normally run on that radius. The belt now is running on this radius, therefore the valve timing relevant to piston crown position was now at an error. This is the clever bit. Within the software, EGR flow is a calculation based on throttle angle position map sensor value, and of course if the valve timing is out, then the map sensor value then is at an error. It's at a different value, although it being only discrete. So in actual fact, the ECU was interpreting this fault as an EGR problem and not a mechanical, physical problem with the valve timing. And I think you'll agree, this engine was near to failure. And the real message for me is, had it not been for NVH in that vehicle, I would not have found this fault. And that really drove home just how powerful a tool this is.
If I can add into that, thanks Frank, is coming back to that E2 value. Traditionally E2 is associated with combustion. It is it's 4-cylinder engine, 2 combustion events per 1 revolution of the crankshaft, but during that road test with no change in load or engine speed, there was still fluctuation in E2, which had to take you to the vibration consistent, certainly with engine, initially combustion, but combustion E2 changes with throttle position. Here we have E2 rising and falling with no change in engine speed or engine load.
Yes, and also if there was a combustion related anomaly, then my take on that would be that some of that energy would then be transferred to E1, the crankshaft, and there wasn't. The actual value of the crankshaft vibration was almost nil, as you can see from the graph. So that's what kept me focused on the fact that it was something related to a component at twice the frequency of the crankshaft. And of course that then led me to the ancillary pulleys on the front end of the engine.
And just in time by the sound of it, Frank.
Well, the other message here is, look, this is a fairly simple engine. We can actually visualize and see all of the components very easily. What if this was a V10 Audi, where it's 20 hours to get the engine out of the frame, just on the suspicion that you might have a front end pulley noise? We can't make those decisions. We have to have hard evidence. And the NVH has provided that evidence for us.
On that point, if we look at the influence of the engine mounting, you could also use the accelerometer as a stethoscope, perhaps place the accelerometer on the engine, measure E2 values there, take them off the engine, mount them on the chassis, look at the comparison between the two. If that engine mounting is performing correctly, there should be adequate suppression of that vibration. I think when you think of how this was detected in a non-intrusive fashion with the accelerometer on the seat bolt,
driver's seat frame,
driver's seat frame,
yes.
It doesn't get any less intrusive than that.
As a development of this, I've now started to use this method to determine, I'm going to use the word combustion anomalies, which can be down to mechanical issues, injector issues, or ignition related issues, petrol or gasoline, with some very great success. It's a very quick means of evaluating the vibration profile from any given vehicle.
So this case study looks at a T3 vibration. You can see from the chart there, T3 lateral vibration, so that's the Z-axis, and this occurred only under acceleration. So let's just clip that all together. We've talked up until now about T being tyre, and that is right. But also it can be other components rotating at tyre frequency. So we're accelerating, T3 almost off the chart, then of course as we level out, take the load off the component here, vibration is reduced. The fault here was the inboard coupling of the drive shaft, so it's a tripod style joint. Now think about the fundamental frequency of this shaft, that would be the same frequency as T1, component rotating at tyre frequency, but we have on the thrust surface of the drive shaft we've got excessive wear. That would introduce misalignment, 3 disturbances per revolution, that gives us a T3. So it's important to think about all components rotating at what is the fundamental T1. You can see T1 there just on the left hand side of the chart. Multiply that by 3, that arrives at the same frequency as our 3 disturbances per revolution of the inboard coupling.
With this kind of issue, be aware of the fact that although we're dealing with a T1 event, to be knowledgeable of the design of the transmission, and of course we would have ruled out wheel and tyre and rim from this before moving on to looking at transmission as being the pure cause of this particular issue with vibration.
So here then we have a customer complaint of whining noise in the cabin. Let's just have a look at this in the signal history. You can see there that we have a road speed and no engine speed. This is a hybrid vehicle. So now we're looking at the transmission driving this vehicle on electric power only. We can see there NVH chart, we've got two microphones. One in the cabin, the blue microphone, that records certainly a peak at about 1,000 hertz, 1 kilohertz. We've also got a microphone closer to the transmission. That is same frequency but greater amplitude. So from that conclusion we say that we are closer to the source based on the level or the amplitude of the sound, the intensity of the sound. So okay, we know this is transmission, but could we drill down further by trying to work out what component within the transmission? So having an understanding certainly of the tooth count involved in the transmission for various components, what do we know? Just go back again. We know that T1 is at 5 hertz. So with that knowledge we know rotation there of in effect what is the crown wheel, that is T1. So if we work out the ratio between the final driven gear, and the final drive gear, we've got 81 teeth on the driven gear, 22 teeth on the drive gear. That gives us a ratio of the counter gear, this gear here, of 3.682 to 1. Okay. We know that on the counter gear, with a rotation now of 18.41 hertz, with a tooth contact 55 teeth, if we multiply the frequency of the counter gear by the number of teeth on the counter gear, that actually comes out at 1.012 kilohertz, 1102 hertz. So now not only have we pinpointed that it is a transmission issue, but we know where to focus our attention within the transmission during disassembly, because quite often these are tooth contact issues that you cannot see. There may be witness marks, they may not. As it turns out with this vehicle, it was a new transmission and it reduced the noise. It didn't take it away completely, it reduced it to a level that was acceptable to the customer. But to be able to drill down to this level without disassembly proves the non-intrusive features of NVH and the amount of evidence that we can present to either customers, technical support or warranty companies.
I think this is a pure example of where an almost impossible decision would have been the result without the use of this evidence. And I think, as Steve has just said, it is impossible to make these decisions because of the financial restrictions involved in doing so.
As a technician, we're all often faced with intermittent problems. This is events that occur very infrequently, very intermittent, no pattern to them. And often customers would bring in recordings of events, whether that be a video or an audio recording. And if we think about that for a minute, that is incredibly useful from an NVH point of view, because if we ask the customer to record an event that's happening with their vehicle when it's safe to do so, we can use NVH software to import that audio recording. Now we have to convert their recording from whatever format they've recorded into .wav, but once we've done that, we then analyse all the data exactly as we would if we'd recorded the same sounds with the NVH microphone. So here we've got an audio recording. You can see it's been imported into NVH. There's two markers there because I know between those markers is where I can hear this noise. Obviously we don't have engine speed, road speed, we have nothing but raw audio data. But if we ask our customer for some key answers to, okay, what was the engine speed? Do you know what road speed you were doing? Do you know what gear you were in? We can almost start picking out key frequencies amongst these peaks. And here we've clearly identified E2 based on the recording from the customer who's told us the vehicle was at the engine was about 1700 RPM in this case. This is customer complaining of a whine from the engine. So that peak we can see certainly that's E2, 2 combustion events for 1 revolution of the engine. Well, E2 is twice engine speeds. We cut that in half. We can determine from this what their engine speed was. We can also determine that peak at E2. Now, is that an offending frequency? It's unlikely, but the key information here is we've been able to capture the audio. we know the engine speed, we know the level of E2, and from that we can make an informed decision as to whether or not this is a component rotating at engine speed, whether it's relative to engine speed or not. If we revert back to a road speed example, if a customer came in with a recording of a noise at, let's say, 100 kilometers per hour, if we know the tyre size, we'll pretty clearly determine where T1 is and use all these product knowledge, the product knowledge that we have in the vehicle to almost determine key amplitudes within this imported audio.
I've often said when using NVH, let's assume, as Steve has just suggested, that we actually don't put any data in whatsoever. Apply the common sense rule that we can almost predict what sort of frequencies the engine will be operating at and what sort of frequencies, let's assume the final drive's around 4:1, what sort of frequencies the tyres and the wheels are going to operate at. And anything between those two figures, of course, will be related to transmission. So even with what I call common sense application, with this information, we can pretty much predict what area we're going to then focus on next.
So with NVH, if you have a PicoScope connected, there's a feature within there called frequency generator. And we can use that to our advantage in a number of ways. But one of the key options that we have is to play any frequency from 0 to 20 kilohertz through the in-car entertainment system, aux socket or Bluetooth, depending on the style of in-car entertainment system. The benefits being helping us to find these elusive rattles, cabin rattles, trim rattles, creaks, squeaks. If we were to set the radio audio volume to a specific level and then play various low frequencies, booming, vibrating noises through the speakers, then maybe we can get the cabin to rattle without even taking the vehicle on the road. The ideal thing is we can do this with the customer present whilst they're in the car, so we can actually concentrate on the rattle that they are complaining of, because it's very easy to go out on road test and think you've identified the same rattle as they're complaining about, but in effect it's something completely different. Remember, we're all different as humans. So this feature, I think, will help hopefully speed up the time required to find these trim rattles and creaks.
I can think of one area where this would be particularly useful. A lot of the high-end vehicles now have got noise suppression technology built in the vehicle design, and therefore being able to create these vibrations with the vehicle stationary, with the engine off, creating these different frequencies within the cabin would indeed help us very much to find out these areas where trim-related issues are incredibly difficult to find.
One of the big areas of NVH diagnosis has to be wheel bearing and the complexities around which is the offending bearing. Looking here, you can see that we've got two microphones, two accelerometers connected to two front hub assemblies, so one mic, one accelerometer, front left and the same front right. Already we can see in the spectrum there that we've got multiple vibrations, all unknown frequencies on the yellow and on the blue. Both of those are connected to the left-hand hub assembly. That happens to be our offending bearing. We can qualify this by playing the audio back and listening to microphone on the left hand, comparing it with the microphone on the right hand. But really what I wanted to talk about is the complexities of wheel bearing diagnosis. Just look at the contamination and the debris on the bearing there, the roller and the race, and the possibilities of multiple vibration orders from just one bearing. Think about the damage to the bearing race, the number of rollers. Is the bearing rolling? Is the roller rolling? Is the roller skidding across the race? So to pull out just a single offending frequency from one bearing, failed bearing, is near impossible. But using microphones and accelerometers in conjunction with one another and listening to the playback and identifying all these unknown peaks within the spectrum, we can call a judgment on which is the offending bearing.
I found that quite interesting because my understanding of a bearing-related type of fault was that you would have a very narrow band of separation. In other words, frequencies which are quite close to each other, varying by a small amount, would normally represent a worn track within a bearing.
So here we look at combustion anomaly, not so much misfire. This is where we've got uneven combustion. And this is a vehicle that had a diesel injector replaced. And everything is fine, idle speed, sort of 1500 RPM, but there was a peak vibration that occurred, I think it's around about 3000 RPM. You can clearly see there, E.5. And the vibration level there, 133 millig, that's an intense vibration to be felt in the cabin. So the software has eliminated a number of possibilities. Whilst T1 and E1 are high, P1, it's nothing compared to E.5, so that's where we would focus our attention. So think about that, a combustion anomaly at 3000 RPM. That creates one disturbance for every 2 revolutions of the crankshaft. So 1 divided by 2 revolutions, E.5. And that's a key peak vibration order to remember, because the majority of E.5 vibrations are related to combustion anomalies. Yes, it could also be components rotating at half engine speed, but think about when this occurs. This was during load, 3000 RPM, and clearly an unavoidable E.5 displayed in the spectrum. At the same time, we could feel the vibration in the cabin.
I find this kind of data incredibly valuable because we often use the word misfire in inappropriate ways. Today we have a lot of issues relating to very serious engine damage because of incomplete or inefficient combustion. And combustion is, in effect, energy being imparted onto the piston crown, petrol or gasoline, and to be able to monitor this very simply from the driver's seat frame is absolutely an incredible tool for a first look, first choice tool when dealing with smooth running issues, as I say, petrol or diesel.
So for further information, we've got picoauto.com, case studies, the software is available there for free. Remember, the software has PicoScope and Pico Diagnostics, which has our NVH software. The YouTube channel for multiple videos, not just NVH, but there are NVH videos there. And the automotive forum, where we have a section dedicated to NVH amongst other running conditions for vehicles.
I'd like to begin the conclusion to this presentation with my greatest thanks to Steve. I think his knowledge of this subject is incredible. I've enjoyed working with Steve. I've learned an awful lot during this video myself, and I hope you've shared in that knowledge. Do remember, look, this is a new generation of opportunity. We're all learning, and of course it offers so much to what we're able to do to diagnose these problems we have with vehicles today.
Yeah, thank you, Frank. I think the feeling is mutual, of course. And I'd just like to pick up on something you said there about we're all on a journey with this NVH. It's, I think it's still in its infancy. If you guys are using NVH out there in new fields, new areas, you're using it for different diagnostic techniques, then please let us know, share the information. We'll put that out on the forum or try and replicate what you're doing in a video. I'd like to close with this statement really, and that is proving what is not at fault can be equally as important as proving what is. You saw there a number of captures where we could eliminate so many components very, very quickly with NVH.
From me, Frank Massey, thank you for joining me. I look forward to seeing you again in the future.
And from myself, Steve Smith from Pico, thank you once again for watching.